The purpose of this lab was to examine a spring mass system swinging in motion. Using Newton's second law of motion and the energy principle, both the motion and the total energy of the spring were predicted in a computational model. The results of the lab are shown in the graphical representation of the motion and the total energy of the system. For this lab, I started out with a video of a spring mass system swinging in motion. Using tracker software, measurements were made of the object's position. The plot displaying the y position of the graph shows a wave function of position versus time. This displays the oscillating up-down motion of the system. By measuring the average time between waves, the time period for a wave oscillation was determined to be 1.53 seconds. Additionally, measurements of the initial stretch of the spring were made and recorded relative to the length of the spring mass system when hanging freely, 0.7 meters. The energy principle relates the effective energy in a system to the sum of its interactions with its surroundings. Choosing the spring mass system, the components of energy included the potential energy of the spring, the potential energy of gravity, and kinetic energy of the system in motion, because no outside interactions acted on the system. Once I had information about the position of the spring mass system and a series of instantaneous time points, using Newton's second law of motion and the momentum principle, I identified the forces acting on the object, its velocity, and updated its position. Additionally, looking at the formula for the potential energy of a spring, gravity, and kinetic energy, almost all of the elements needed to calculate the instantaneous total energy of the system were previously identified. With the position data taken from Tracker, I created data about the x and y positions of the object in space for instantaneous times, t. From this data, I identified elements of the velocity and net force to make predictions about the position of the spring at each time. The question posed was how could the total energy of the system be predicted with each instantaneous time t? The equations for the elements of energy of the system are shown here. From the position data created from Tracker and other given assumptions, we know everything about the system except for the spring stiffness that makes up the spring's potential energy and spring force. The formula for the time period of an oscillating spring is directly related to the mass and stiffness of the system. Rearranging the formula for the time period k was solved for and determined to be 6.83 newtons. Once I had identified my initial parameters and conditions of the spring mass system, I created a code that would model both the updated position and total energy of the system. The first part of my code includes initial conditions about the location and energy components of the system. The second part of my code includes two while loops. Using Newton's second law, the first part of my while loop updates the instantaneous velocities and position of the model spring based on the calculated forces acting on the mass. Using the energy principle, the second part of my while loop updated the instantaneous kinetic spring potential and gravitational potential energies of the system. This is given by updating formulas about the individual and total energies of the system. When the code is run, the visual representation shows a spring mass system that starts from an initial velocity of 0 and experiences changes in velocity and position depending on the magnitude and direction of the gravitational and spring forces acting on the system. The blue dot represents the movement of the spring mass system as it's updated by a computational code. The red dot shows the motion of the spring mass system as taken from points recorded in the tracker software. A graphical comparison of the blue and red dots' motion is shown on the wave function above. The graphical comparison shows a very strong match. Areas of variance were explored in the breakup of the x and y oscillation curve. The total energy of the system is represented by the second wave function that shows the kinetic energy of the system in blue, the spring potential energy in red, and the gravitational potential energy in green, and the sum of the energy components in yellow. And comparing the x and y oscillations of the graphs, points of variance or error can be accounted for on both the x and y positions of the graph as it varies with time. While the predicted motion compared to the observed motion shows a close match, the advancement of the x position made by the computational model versus the observations is consistent. A shift in the height of the predicted motion indicates that the computational model is constant in over-predicting the x position of the graph. This is also true for the y position of the graph. Because the only force components acting on the system include gravity and the spring force, and while gravitational force of the system is its mass times the gravitational constant close to Earth, the error of over-predicting the graph is likely in the spring force calculations of k. To solve for k, the average of the time steps was taken. Had the specific instantaneous value for k, as it varied with time, been used in the calculations for the spring force acting on the system, the computational predictions and observation would be more closely aligned. What does this mean? For the spring mass system, the change in energy of the system equals 0 as represented by the yellow line on the graph, which means the total energy at the beginning of the motion is equal to the total energy at the end. In this lab, the change in total energy of the system is zero, regardless of the change in individual value changes in the energy components for the system.